Alright, welcome in today's class, everyone. This is Chemistry 1000/1010. Okay, so we're going to be solving questions, different questions on in chemistry. Okay, so in your preparation for your test 1, we're just going to look at different questions. So our first question of today is asking us to say that a white powder is analyzed and found to contain 43.64% phosphorus, okay, and 56.36% oxygen by mass, okay, by mass. What is the compound's empirical formula? So when they ask you this question, you need to understand that when they're asking you to find empirical formula, then they give you percents. These percents, you can just take them to be what? To be grams. Okay? You can just take them to be mass because they said it is 43.64% phosphorus by mass. Then they said 56.36% of oxygen by mass. So that is one thing you need to note. Okay? So what you're going to do first is that you're going to get the two atoms which have been mentioned. So they've mentioned phosphorus, okay, and they've also mentioned oxygen. Okay, so now the phosphorus, they've said that it is 43.64%. Okay, and then so just put this. So here, the oxygen, they've mentioned that it is what? It is 56.36%. Okay, that is what we've gotten. So now the first thing you're going to do is you're going to change this to grams. Okay, so you're going to have 43.64 grams to 56.36 grams. Okay, so after doing this, you're going to divide by the molar masses of each of these atoms, phosphorus and oxygen. So just help me with your periodic table. What is the molar mass of phosphorus? Anyone?
30.97376.
So 30 point
97376.
97376. Okay, this is in grams per mole. Okay. So even this side, what's for oxygen? It is what? 15.99. What's the other one? 94. Like this?
Yes.
All right. So now after you do this, you're going to divide. Okay, when you divide this side for phosphorus, you say 43.64. You divide it with the 30.97376. okay, you get so 43.64 divided by 30.97376. okay, we are getting 1.408. Okay, so we're getting this, so meaning that I'll write up to let me just write it first of all. So I get 1.4089353 moles. Okay, then this side I am getting, so 56.36 divided by 15.9 9994, okay, which I am getting a 3.5226320099. Okay, so of this I'm going, so this one is also in Morse, so I am going to divide with the smallest, okay, of the two. So if there are three, meaning that I'm going to divide the smallest of the three, but here since I only have two, okay, I only have two, so I'll divide the smallest of the two, which is this one. Okay, so in here it is 1.40893,453, okay, which is in Morse. Even this side do the same thing, which will be 1.40893,453. okay, so when you divide by that, this side, because this side is going to be, we know that this one is going to be what? It's going to be 1. Okay, to this side, when we divide with the 1.40893,453, it is giving you a 2.5. Okay, so now if I was to ask what would be the, so I have 1 to 2.5. I know it's continuous, but if I round it off, it will be 2.5. okay, it's something like this. So it's continuous, so I've rounded it off, that's why I've left it here. So what could be the empirical formula of this? Anyone?
P05. P205.
Yes. So someone might think just to say, okay, let me round off the 5, it becomes a 3. There you get it wrong. Okay, so you need to understand that if you have a 0.5, maybe it was 1.5, a number which is not 6, but it is like 0.5, something that is giving you 0.5, you have to multiply that by 2 so that you can get the correct answer. So in this case, since we have P, which is 1, okay, and then we have the oxygen, which is 2.5. So we don't want this 2.5, we want it to be a whole number. So you can make it a whole number by multiplying this by 2. As a result, it is going to be equals to 2 to what? To 5. This is just telling us that the phosphorus here, it is 2, and the oxygen, it is 5. Okay, therefore the empirical formula is equals to P2 oxygen 5, and you are done with the first question. Clear?
Yes. Yes.
I have a question, sir.
Yes, you're welcome. You are free to ask.
So what if we had a number like here, 2.6, 2.7, or 2.3, 2.4? Which factor should we multiply it for us to get a whole number, or how can we do it?
Okay, so if you had something like 2.7, definitely this number is just telling us, because it's telling us that the number is close to what? To 3. So it is just moving it to, it's better you just move it, becomes a 3. There you just, so if it was 2.6, 2.7, you would have rounded it off to become, this one would have become a 3. Okay, but if it is 5, you don't round it off, you multiply by a factor that is going to make it a whole number. Okay, so if you had something like yes, let me even explain here. If you had something like 2.4, 2.3, those ones you have to round it off. Okay, and for example, so 2.4, 2.3 going down, you round it off because those numbers are not 5. Then this side again, if you have 2.6, 2.7, 2.8, just round it off. Okay, there's nothing like multiplying by a factor, but you can only multiply by a factor. For example, if you have 0.25. Okay, again, if you have something like 4.25, so you know that for this to become you multiply by 4. Okay, so as long as it is those numbers that are direct to say, like, you can multiply by a certain number to get a certain result, those numbers you have to multiply by a factor. But if you are 2.6, 2.7, just round it off, your answer will be correct. Clear?
Yes, sir.
Yes. So if you had something like 1.49, this is definitely telling you that this is something like 1.5, right? Yes. So if it is 1.5, you multiply by what? You multiply by 2, as a result to give you a 3. So that is one thing you need to note when you're dealing with empirical formula. Okay. Now, let us go to the next question. So now, I'm going to open this question to everyone so they can respond their opinion on the question. The question is saying, what is the bond angle of BH3? So I'm opening this question to everyone. So what is the bond angle? And just give us a brief explanation on it. To why? Or if you want to try, just you're free to try. Just tell me the bond angle, even if without explanation.
Sir, may I know that the bond angle is 120?
What?
The bond angle in this for this compound is 120 because of its molecular geometry.
Okay, so what's the molecular geometry for this one?
Trigonal planar.
Yes, wonderful. So the bond angle in this case, it is 120 degrees. Okay, 120 degrees, that's the bond angle. So because she has explained to say, okay, we have the geometry, okay, like this, that is so here we have H, okay, and this one, so here we have 120, you can just say it like that. It's the bond angle is 120. Okay, so she has also mentioned to say that this is trigonal planar. Okay, so that is correct, and no addition, no subtraction. Okay, so this is the bond angle is 120. So now on this question, I'd prepared to say I'll ask you some questions on it because I want to just get some. So on one question, so you have a molecular structure to say this is ammonia, okay, then this is ammonia, right? Or let me not write it here so that I don't affect the answer. Let me just write it on a different page. Okay, so on this part I want to explain something. Let's say you have ammonia, you have ammonium. Ammonium is like this. This is ammonium, okay, and ammonium has a positive charge here. Then you also have ammonia. So this is ammonium. Then here you have you have ammonia. Then here you have I think this is amide. Okay. Say it like this. Okay, so now in this case they ask you to find what's the bond angle of this one. Anyone?
One 109.5.
109.5. This one? For ammonia, anyone?
$107.
Okay. Then this one? Anyone? This one? Which structure does it look like? There's a structure which looks like this. For example,
It looks like water.
looks like water, right? So, and for water, what's the bond angle for water?
$104.9.
104.5. Okay, have you noticed something that is happening here? And mind you, all these structures, if you were to try to make like they are all tetrahedral. Okay, just that they have different names. You have this but in the general like the geometric the geometry, they have a tetrahedral structure. Okay, but in tetrahedral you have different, like for example, so here this one is tetrahedral, like this is complete. Okay, and then this one again, if you try to check, it also has like 4 parts. Okay, where it can, there's this part, this part, this part, and this part. So even here it's like this. You've seen even the lone pairs, they also create a certain geometry of the structure. So you've seen that they are all falling in a 4 structured structured way. Okay, so they all have different names. This one, it's a bent. Okay, they call it a bent V shape because that's what it's even talked about, like for the bent V shaped, like water. Okay, but water is also tetrahedral. It's tetrahedral, but the exact shape, it's bent V shaped. Then ammonia again, it's also tetrahedral, but it has a lone pair, so it causes it to have a certain shape. Just forgetting exactly what the name is, but it is creating a certain shape. Then this one is a general tetrahedral. Okay, tetrahedral. That's the geometry of it. Now, you've noticed that here, okay, what you're going to notice is that here, if you check, this one it never had any lone pair, right? The bond angle was 109.5. So if it doesn't have a lone pair like this one, it is 109.5. If it has one lone pair, it loses, you subtract it by 2.5. Okay, so when you subtract it by 2.5, you get 107.5 or 107, and that is the one with one lone pair. If it has 2 lone pairs, okay, it changes the structure. You've seen the way it is. You also subtract minus 2.5 and you get the 104.5. Okay, have you seen that?
Yes, sir.
Yes. So that is what I just wanted to show you. So it's falling under the class of a geometry which has 4 shape, like 4 sides. Yes. it is falling there, but it's even if it's falling there, there is some difference in the bond angles. Okay, so they can ask you in multiple choice question, what's the bond angle of this? So that is one thing you need to note in your mind as you'll be solving such a question. Okay, so otherwise the main question was this one. I got it from a past paper. Okay, now let us solve the next question. Answer the following question based on xenon F4. Okay, so here we have xenon fluoride, which is xenon with fluorine, which is 4. Okay, now they're telling us to draw the Lewis structure of what? Of xenon. Okay, so now when you're drawing the Lewis structure, the first thing you need to ask yourself is what is the first step? Okay, so now the first step, you've gotten your xenon. Okay, xenon which is with fluorine here. So this is a compound. This is the molecular formula of it. Now the first thing you do, it is to find the valence what? The valency electrons of the total valence electrons of this compound. Okay, so number one, you calculate the total valency electrons. That's the first thing you're going to do, the total valence. So you're going to say that the valence electrons is equals to so here you have xenon. So now valence electrons, they are those electrons that are found in the outermost shell. So in this case, xenon, which group is it found in? Anyone? If you check the periodic table, where is it found? So you're going to find out the group 8, right? So yes. So it in group 8, xenon, that's where it's found. So meaning that the outermost shell electrons are what? They are 8. So you say 8 for xenon plus. Okay. Now you go to the fluorine. Fluorine is part of group 7. So you're going to say how many fluorines are here? There are 4. So you're going to say 4 times 7, or you can just say 7 plus 7, since they are like this, since it's the same as xenon plus F plus F plus F plus F. You can just say this is 8 plus 7 the first fluorine plus 7 the second fluorine plus 7 the next fluorine and plus 7 the last fluorine, and you've gotten all of them. So after doing this, you check, do you have an ion? So if I had a positive ion here, I would have subtracted by 1. Okay, if I had a negative, I would have added a 1. That's how it is. Okay, because when there's a negative, meaning that it has gained. When there is positive, meaning that it has lost. So keep that in mind. So if I add 8 plus 7 plus 7 plus 7 plus 7, what I am going to get, it is going to be 36 electrons. Okay, so I've gotten the 6 electrons. Number 2, I am going to do what? To choose the central atom. Okay, so you choose the central atom. How do you choose the central atom? So the central atom is the atom with what? It is the atom with the least electronegativity. Okay, it is the one with the least electronegativity. So, or of the two, so the least electro so of the xenon fluorine, which one is the least electronegative?
Xenon.
Okay, so you get the xenon. That will be what? Your central atom. Okay, so you have xenon here. Let me do this. So you have xenon. So now this xenon, now you have 36 electrons. Okay, so these 36 electrons, so remember, you don't only have xenon as the only atom, no, in this compound. No, you also have fluorine. So now what do you do with the fluorines? You need to connect these fluorines to the what? To the xenon. Okay, so when you're connecting the fluorine with the xenon, you need to add a bond. Okay, so now you add a bond to say, okay, when you add a bond to say like this, you add the fluorine here, then like this here, you add the fluorine, then like this, you add the fluorine, and like this, you add a fluorine. Okay, so you've connected all the atoms here, because remember that a bond, it is representing 2 electrons. Okay, that in mind, don't forget, a bond is representing 2 electrons. So if you have this compound, you've connected, after you've connected all the atoms to the central atom, what you're going to do now, it is to make sure that these atoms which are here, okay, you can check them like these ones, the fluorine, the fluorine, the fluorine, the fluorine, they all have to follow the 2 rules to say there is the duet rule, okay, and there's also what we call the octet rule. Okay, so this one mostly is for hydrogen, and then this one, it is for because this one deals with 2 electrons. Okay, that's the rule mostly used in hydrogen. This one is talking about 8 electrons, meaning that for this to be balanced, it needs to have 8 electrons. So now we have a total of 36 electrons, and we've used 8 of them. We've used 1, 2, 3, 4. Okay, that is what we've used. Now, of these 4, they are representing 2, 2, 2 electrons. So meaning that 8 electrons we've done what? We've used. So we're remaining with the here we have, so there's 7, 7, 7, 7. So here we're remaining with in short, we're just remaining with 28 electrons. Okay, that is what we are remaining with. So you start balancing these. So let me just rub here. This is too big. Okay, so the fluorine is here. So now I start adding electrons here. I'll add an electron there. I'll add an electron there. Oh, I'll add these 2 lone pairs. Even here, 2 lone pairs. Then even here, I'll add this. Here also, I'll add those. So now I've used 12. So of the 28, I've removed 12, meaning that I'm remaining with 14. Now of the 14, I'm going to find out that here I'll add 6. I'm remaining with 8. Of those 8, I'm going to add again here on fluorine. I'll add. So after adding, I'm remaining with 2 electrons, because this is in short, this is like, so how many have I used? I've used here they are, so here there are 2, 2, 2, 2, 8. 8 plus 24, that is a 34. So now I'm remaining with 4 more electrons. So those 4 electrons, where am I going to place them? Anyone? Where am I going to add the 4 electrons which are remaining? Because I've used up 32
On the set.
on the central atom, right?
Maybe. The central atom.
Yes. So we add those ones on the central atom. So now remember that they are not. It's not every structure that is going to be following the octet rule. Okay. So there are some exceptions. There's some exceptions, like for example this one. You're remaining with 4 more electrons, and all these 4 electrons are supposed to be on the what? On this structure. So what you do is that the remaining electrons, you add them here. Okay? They will become lone pairs on the central atom. So I'll add here, and I'll also add here. Okay? So when I add here and also there, what I'm going to realize is that I've now utilized all the 36 electrons. Okay, so after I've balanced these ones, all of these are balanced. For fluorine, it is balanced. It is following under the what? The octet rule. This one is also balanced. Octet rule. Octet rule. Octet rule. But the central atom, it is xenon. Okay, there are some structures they don't follow. They're not going to be following the octet rule. Okay, and if you are to show the geometry, because here you can check what's the geometry of this one. Okay, you're going to find out that it won't, if it never had these ones. So let me just change. Okay, so if it never had these ones, it would have been called what? What would it have been called? Anyone? So that we move to another question. Is everyone there? Okay, so if you never had those lone pairs, what would have been called? Like this one, the way it is. What is it called?
Tetrahedral.
Yes, it's tetrahedral, right? So now, after now, it has the lone pairs, because it needs to have the lone pairs for it to be complete. Okay, so you add lone pair there. As a result, because of these lone pairs which are here, it has changed now, because if you try to get the molecular, you find out that the lone pairs will have that, even this one here, even this one here, and then this one here again, and then this one here again, and this one here again. So if you count them, they are 1, 2, 3, 4, 5, 6. So if there are 6, it becomes an octahedral. Okay, so that is one thing you need to note. Okay, so this one, it has also changed. It has these lone pairs which are here. So this is now the structure. This one does not follow the octet rule. Okay, you can see this one has about 2, 2, 4, 6, 2, 4, 6, 8, 10, 12. Okay, there are 12 electrons on one atom. So that one does not follow the octet rule. Okay, there are exceptions. So now, let us, and the next question is part of the same question. Okay, so the next question is just telling us to say how many bond pairs and lone pairs are in the xenon 4. Okay, xenon F4. Okay, so what do we have? So now you just start calculating them. The bonding pairs, you have 1, 2, 3, 4. Okay, so the bonding pairs, these ones, the ones who are bonding, they are the bonding pairs. And then these ones are the lone pairs. That is what you need to note. Okay, so meaning that if you are to calculate the lone pairs, they didn't specify. They can ask you to say in the xenon, But this question was not, if I don't know if they wanted us to find for xenon only, but if they just said in xenon F4, meaning that it's for the entire compound. Okay, so if you're doing for the entire compound, xenon 4, you calculate the lone pairs. In this case, we have lone pairs. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so they were so for the entire compound, so I'll just write them. So entire compound, which is xenon F4, they are 14 lone pairs. Okay, now after the 14 lone pairs, we also have the bonding pairs, which are 1, 2, 3, 4. So they are 4 bonding pairs. That is one thing you need to note. Okay, now if they ask you to say for xenon, okay, for xenon, what is the bond pairs and the lone pairs in xenon, like this one, xenon. So you'd have just gone to the central atom there, which is xenon. So xenon, which has 2, 2, okay, so those are the 2 lone pairs, so they are 1. So you don't calculate to say that there are 2 here, so you calculate to no. You say 1 because a lone pair, it's a pair because they are 2. So it's just 1 lone pair. 1 lone pair. So it's 1, 2 lone pairs. So for xenon, you just say they are 2 lone pairs. Okay? Then for the bond angle of 1, 2, 3, 4. So they are 4 bonding pairs. Okay, are we together?
Yes, sir.
All right. So that is one thing you need to note when you're dealing with Lewis structure. Okay, so a question might come on this. So
Sir.
just, yes.
Where are those 14 lone pairs coming from?
So the 14 lone pairs, I calculated, since they said, for example, when they say this question over here, okay, it's saying that how many bond pairs and lone pairs are in. Okay, so there is xenon F4, because xenon fluoride. Okay, so now this xenon F4 for the entire molecule, so here we're just calculating for the entire molecule the lone pairs that are there. Okay, for the entire molecule, so we calculated lone pairs of the fluorine, the xenon, we calculated all of them. Okay, we were counting them in short. Then if this question specifically was asking us for the central atom, the central atom only had 2 lone pairs. Can check here. Okay, so that's why we calculated them to be 2, 1, 2. Okay, there are 2 lone pairs, and the bonding pairs, they are 1, 2, 3, 4. Okay, so the 14 came from the entire molecule, which we calculated for everything. And then for this one is for the central atom. Clear?
Yes, yes.
All right. Okay, let us move to a different question. This question is asking us to say, calculate the standard free energy change for the following reaction at 25 degrees Celsius. Okay, so here we have gold, okay, 2 gold plus 3 calcium ions. It changes to so this one is it's in aqueous. Okay, so instead of just writing aqueous, they wrote that. So this is aqueous as well. Okay, don't let it confuse you. So now the question is asking us to say, calculate the standard free energy, okay, change for the following reaction at 25 degrees Celsius. Okay, so don't forget about the constants which they will give you. Okay, so now the first thing you need to note is when they talk about standard free energy, what are they talking about? They are talking about the Gibbs free energy, okay, which is gotten by saying that Gibbs free energy is equals to negative NFE. Okay, so where the F is the Faraday's constant, so Faraday's constant, which is 9 is it 96485? Can just confirm on that, which is coulomb per mole of electrons. Then we have N, which is the number of electron transfer. Okay, then we have the E, which is the what? The E cell. So this is the formula that you're supposed to use. Are we together?
Yes, sir.
All right. So this is the formula for standard free energy. So they specified to say at 25 degrees Celsius. So you just confirm with this, but I'm sure it's correct. This is the one, 96485. So they'll give you these constants. Okay. Now, when you're solving this question, so you have a reaction. So this reaction involves God. Okay, they said that 2 God, okay, which was a solid, plus calcium 2 plus ions, okay, which was in aqua, so they wrote 1 molarity. It was giving us so here the calcium had 3, then now it had God, which is Au 3 plus, okay, and then it was in aqueous. They just wrote 1 molarity plus the calcium, okay, which was 3. Then this one was 2. Okay, all right, like that. So now the first thing we need to do is to identify which one is undergoing oxidation. So of the 2, which one is undergoing oxidation?
Calcium.
No.
God.
Yes, it's God. Okay. So here, the God 2AuS is undergoing oxidation. Okay. You can check that it was God solid at the start, then it became 2 Au 3 plus. So remember that oxidation is an increase in what? In oxidation state. Okay, so it has increased from 0 to 3 plus. So it is what? It is oxidation. So meaning that if you are to try to add the electrons which are being transferred here, they are so since this one is already balanced, you need to check the difference in the electrons. Okay, so here there is a 0 here. Okay, so 2 times 0, it is 0 this side. Then this side it is 2 times the 3 plus, it becomes 6 plus. Okay, or 6 electrons. So 6, there's 6 here and there's 0 here. So 0 minus 6, it will be negative 6. So the negative is just telling us that it is losing 6 electrons. Okay, for each to get to this side. So because it's just telling us that, you just get the 6 and you add it to the side with the highest what? With the highest oxidation state, which is this side. 6 electrons. Okay. Then you go to reduction. reduction. Which one are going with reduction? The calcium. So it's 3 calcium. So these two are the ones which has made this to be 6. Otherwise, if these two wasn't there, it would have been 3 electrons. You know that. Okay, it would have been 3 electrons. Here, it would have just been 3 electrons. But because they've already balanced it, so this process has already been done. Okay, the multiplication, where the 2 came from, they've already done this. So because they've already done this, you can just write this. There's 2 here, there's 2 there, so that we don't take much of space. Then now, this one is aqueous. It was 2 plus, and then it reduced in the oxidation state, so meaning that it was undergoing what? Reduction. So it became calcium, okay, which was solid. So 3 calcium. Then now, so it's going to be plus 6 electrons, and then it is giving us 3 calcium, okay, which is a solid. So now you've already seen what was happening now. Okay, they cancel the electrons, but let me just reach here. So now I said that Gibbs free energy is equals to negative N F, and then there is E. Okay, so the first thing we need to calculate, it is for the E cell. Okay, the E cell, let us calculate for it. So E cell, you just say E cell in this case is equals to E cathode. Don't forget the formula. E cathode plus E anode. Okay, let me show you how to use it now. So you need to understand what happens at the anode. So if I was to ask what happens at the anode and what happens at the cathode.
At the cathode, there is a reduction that they expressed.
At the cathode or at the anode?
Oxidation.
So here it's what?
For cathode is a reduction.
Okay, reduction. Then this one?
Yes, we keep the calcium or gaining 6 electrons.
Okay, wonderful. So here the cathode, it is what? Reduction. Anode, it is, so you've seen the formula I've used. There are 2 formulas. I'm sure you've seen in zoomed out. There are 2 formulas to say there is E cathode minus E anode. There are 2 formulas. Okay, so whichever formula you're going to choose to use, you get the same answer, but how to apply it, it is where there is much key information which is needed. So when you're applying these formulas, you apply them differently. So if we're calculating E cell, we need to have an E cell value for the E what? For the E cathode. Okay, so now we come back here. So here they've told us that these are standard reduction potentials. Okay, you've checked here. There is God. So this one here, it is telling us that God 3 plus, so it's going to be like this. God 3 plus is changing to what? To God. Okay, so this is just telling us that it is gaining 3 electrons to do what? To become God, like this. That is what is happening. So now the E cell value is 1.50 volts. Okay, so and then again they're telling us that you've seen that this is calcium 2 plus. So the one they've started with, it is what they've started with. So it's calcium 2 plus. It is becoming what? Calcium. So it's becoming calcium, and the E cell value is negative 2.87 V, like this. Okay, so now it is also this one is gaining 2 electrons to get through this. So now here we've identified that the ones undergoing oxidation, it is what? It is God, right?
Yes.
So if we were not given this expression to show us how the reaction is happening, what would have done is that we would have changed the smallest, okay, which is which one? Which is this one, the calcium, to become an oxidation reaction. But this one, what we are seeing here is that they've already told us that the one which is undergoing oxidation from the equation, okay, we are able to see that the one which is undergoing oxidation, it is what? It is gold, not the what? Not this one, not the calcium, okay. So meaning that we need to change the one for what? For gold, because if we were to change the one for calcium, just depending, because this one is smaller, because under normal circumstances we are supposed to change this one, okay, we're supposed to change it so that it becomes oxidation, because both of these, you can check, they are both gaining electrons, so meaning that they are both what? Reduction reactions, okay. So this one is the one undergoing oxidation, so meaning we're going to change it to become an oxidation reaction. It is going to become, this one will be Au, so we switch it, okay. It's going to become Au is giving us Au 3 plus 3 electrons, okay, meaning that even this is also going to change. It's going to become negative 1.50 volts, okay. So you've identified that this is the one at the anode, and then this one is the one at the cathode. So meaning that at the cathode you have negative 2. So you have negative, so in this case, if I'm using this formula, I'm going to say E cell is equals to, the E cathode is negative 2.87, okay, volts, plus, okay, I'll get the E anode. So you've seen that after I've added the plus, this one became negative, okay, so it's going to be negative 1.50 volts. So it's going to be plus negative 1.50 volts, okay. As a result, E cell will be equals to negative 2.8, oh yeah, okay, 2.87 volts minus 1.50 volts. Then the E cell value is going to be equals to negative 2.87 minus 1.5, which will give us negative 4.37 volts. Now if you're using this formula, what you're going to say is that E cell is equals to, what's the E cathode? E cathode, you get the one we've identified, okay, we've identified the one is undergoing what? Oxidation, and the one which is undergoing what? The ones undergoing oxidation. So at the cathode there's negative 2.87, okay, negative 2.87 volts. Then you're going to say minus. Now what you're getting at the E anode, you're not getting the one you've changed to say negative here. No, you don't get that one. You get the one which has not been changed, which is what? 1.50 volts, which was given in the question. That's when you use that formula. So here I'll say minus 1.50 volts. As a result, it's going to give me the same answer, which is just negative 4.37 volts. Are we together?
So I'm not clear on how you identify which formula to use.
So on the formulas, you can use any, but on applying them, that's where the important thing is.
Okay, sir.
Yes, you can use any. If you want, you can use this one, or you can use this one. So me, I like using this one because what I do is that when I change a reaction, I also change the what? The voltage. I also change it. Okay. Okay, so which makes me easy for me. I can just start plugging in. But if I just want to use the same way they are here without changing, but I've identified the one undergoing oxidation and the one undergoing reduction, I can just do this. I can just say, okay, I'll just get the same way they've given me and use the second equation here. Okay, clear?
Yes, sir.
Okay, so we've only done this for this question because you can check. The question is saying that calculate this standard free energy change for the following reaction. So this one is being converted to this one. Okay, that's why we've done this. Otherwise, under standard protocols, we're supposed to change this one, the one which is less, which is negative 2.87. If it was, because this one is already telling us that it is under non-spontaneous reactions. Okay, it's already telling us that. Okay, but if it was under those normal reactions which happen like under the galvanic cell, we were supposed to change this one. But for this question, what we have is that they're telling us that gold is the one undergoing what? Oxidation, and the calcium is undergoing reduction. Okay, we're not yet done. The question now is finding the Gibbs free energy. So you just say change in energy is equals to negative N F E, and then change in G is equals to negative, what is N? N is the number of electron transfer. So how many electrons have been transferred? 6 electrons. Okay, so you're going to say 6 electrons have been transferred times the 96485 coulombs per moles of electrons. So in short here, this one is not supposed to be negative 6. Let me say it's supposed to be negative 6 moles of what? Moles of electrons. The one that's been transferred times the E cell, it is negative 4.37 volts. Okay, so this negative and this negative become positive. Then change in G is going to be equals to 6 times the 96485. It's going to give us, so these moles of electrons go, and then now the change in Gibbs free energy is going to become
Sir, I have a question.
yes.
When you're picking the numbers of electrons, are you supposed to pick the side which is undergoing oxidation or the one which is undergoing reduction? Which one do you supposed to pick?
So the side you're supposed to pick is the ones which are balanced. Like when you balance them, not like so you've seen that they've already been balanced. There are 6, even here there are 6, right?
Yes.
So the ones you pick, you don't just get to say, for example, if this one was 3, for example, there are 3 here there are 2. Let me say the reaction was like this. Okay, normally the reaction would have been like this or like this. Then the other one would have been calcium 2 plus 2 electrons, and then it's giving us calcium. So you've seen that these are different, right? So because they are different, you need to, and the reactions are not balanced, so you need to balance the number of electrons by multiplying this one with a 2. That's how it came to be like this. So they multiplied with a 2 here, then this one at the bottom they multiplied with a 3, so that they can have these. As a result, they ended up having this. Have you seen that?
Yes.
So now when they ended up having this, they found out that after they've balanced the electrons, these are the electrons which were transferred for it to be a complete reaction. So meaning that 6 electrons is the number of electrons transferred. Clear?
Yes, it's clear.
All right. So meaning that when the Gibbs free energy, when you multiply everything here, you're going to get an answer which is 2529 836.7 joules. Okay, and you've seen that it is positive. So what comment would you give for such a reaction like this one, the way it is? Is
It's
it
a spontaneous reaction.
It's a what?
It's a
Spo-
non-spontaneous reaction.
Yes, it's a
None.
non-spontaneous reaction because of it's positive. If it was negative, it would have become spontaneous. Okay. Otherwise, wonderful tries, wonderful, wonderful, everyone. So don't forget this. Yeah. So if you want, you can write it in kilojoules. You can just say this is the same as 2.529. You can just write this is the same as 2500 to 9.8367 kilojoules. Okay, you can do that, it's also fine. Okay, but even there it is well and good, and you're done with this question. Okay, clear, everyone? Are we clear?
Yes, sir.
Yes,
All right.
sir.
Okay, so now let's look at the last question. Yes.
So I wanted to ask on the units there. Was it not supposed to be joule per mole?
Joule per mole.
Or is just okay writing just joule like that?
Yeah, I'm sure it's fine. I'm sure it's fine. Yes.
Oh, thank you.
Because Gibbs free energy, it's energy. Okay, it's energy. I was trying to cancel out the units because the moles has cancelled these moles of electrons. Okay, but I'll comment after. Let me just confirm with it. Okay, but you can just leave the answer there, I'm sure. So now there's this question to say a galvanic cell consists of magnesium electrode in a 1.0 molarity magnesium nitrate solution and Ag electrode in a 1.0 molarity of silver nitrate, okay, solution. So now they ask us to calculate the standard EMF of the cell at 25 degrees Celsius, given that E cell E value for, so they've told us that E value for Ag plus being converted to Ag, it is what? The E cell value is equals to 0.80 volts. Okay, so this is where I'll explain what I was trying to say there. So you've seen that here Ag plus is being converted to Ag. How many electrons have been gained here? It is 1 electron. So you say plus an electron where it is big. Okay, to show that it is a standard reduction potential there. So then now here again you have magnesium 2 plus, you can check it is being converted to magnesium. Okay, and the E cell is equals to negative 2.36 volts. Then here there is 2 electrons which have been transferred. So now when you have this, you've seen that both of these reactions, they are both what? Reduction. Okay, are we able to see that, everyone?
Yes, sir.
All right. So these are reduction reactions. So for you to find the E cell, because when they talk about EMF, it is just electromotive force. Okay, so electromotive force is just voltage. So in short, they're just asking us to find the voltage or the E cell value. And remember, the E cell value is calculated by saying E cathode plus E anode. Okay, this is the formula I like to use. So now I need to choose which one will become my my cathode and which one will become my anode. Okay, so now looking at this the way it is, both of them are reduction, and you know that at the cathode, that is where reduction takes place. Okay, and at the anode, that's where oxidation takes place. So because that is the case, you're going to realize that since reduction occurs at the cathode, oxidation happens at the anode, what you're going to realize is that you need to have both reactions. You don't only have supposed to have reduction. So now of the two, you're going to ask yourself, which one are you going to change? Because both of them are reduction. So now of the two, which one are you going to change if I was to ask, and why?
Magnesium.
Magnesium, right? Why?
Because we don't need to have, because this one is less spontaneous. We don't need to have a negative EMF. Always we need to have a positive EMF.
Okay.
So if we we need to change magnesium so that we have a positive answer.
Okay, thank you for the contribution. Okay, wonderful. So what we are changing is the negative 2.36 volts, correct? But what I wouldn't agree on is on the reason. Okay, otherwise the answer is correct you've given me. We're changing this one. So for example, if we had 0.20 here, instead of having this, we had this. What are you going to do? Yes, I'm hearing someone wants to ask.
You change the smaller one.
Okay, wonderful. Yes, that's the reason I wanted. Otherwise, thank you very much for the contribution. That's very wonderful. Yes, so you change the smaller one, okay, to become an oxidation reaction, and in this case the smaller one is the one which is negative. Okay, the negative one is the smaller one. Okay, so this one is going to be negative 2.365. so when you change it now, we are going to have silver plus electron transfer. It's going to give us the silver. And then we have the magnesium. When you change it, this one comes this side, both of these two come this side. As a result, you're going to have magnesium is being converted to magnesium 2 plus 2 electrons. Okay, and then now the E cell for the silver, it will be the same. Okay, and then for the E cell of the magnesium, it's going to change. It's going to become what? It's going to become positive. Okay, so it's going to be 2.36 volts. Okay, as a result, you're going to say that now E cell is equals to E cathode plus E anode. As a result, your E cell will be equals to, what's my E cathode? My E cathode is 0.8. Okay, 0.80 volts. Then plus my E anode, since I have changed it, so since I'm using this formula, okay, what I'm going to do is that I'm going to get the one which has been changed, which is 2.36 volts. As a result, my E cell, which is my EMF, is going to be equals to 0.8 plus 2.36, which will be a 3.16 volts. and this will be my answer if I'm using this formula. Or you say E cell is equals to E cathode minus E anode. Then you say E cell is equals to E cathode. What is my E cathode? So this one, that formula, I've written the second one. I don't need to do all these things. Okay, I don't need to do all these things. What I'll just do is that I'll come here and I'll just say, okay, which one is smaller? This one is smaller. Okay, this one is undergoing oxidation, so it will become my anode. Then this one is big, so it's going to become the cathode. That's what you're going to do only. Then you're going to get the E cathode, which is 0.8. You say 0.80 volts minus the E anode. What is happening at the E anode? It is negative 2.36 volts. So you're just going to get even the negative. So it's negative 2.36 volts. Then as a result, you get to have the E cell to be equals to 0.80 volts plus negative 2.36 volts. As a result, your answer becomes 3.16 volts, which is just the same answer. So how to apply it, it is what is very important when you're dealing with such questions. Clear?
Yes, sir.
All right. Okay, so this was the last question we had in these questions which I had prepared. Okay,